Imagine you're on a spaceship, not one of those sleek sci-fi things, something impossibly fast. Fast enough to cross the Milky Way in an afternoon, fast enough that galaxies become blur of light in your rear window. You pick a direction, any direction, and you just go. You pass stars, then cluster of stars, then entire galaxies, great spirals and ellipticals, each one with 100 billion suns, sliding past you like mile markers on cosmic highway. You keep going. You pass the last galaxy. The light behind you fades. Ahead of you is nothing, just blackness. And then you arrive at the edge of the universe. What do you see? A wall, some kind of shimmering boundary, a sign that says, "That's all, folks." Now, here's the thing, you don't see any of that because there is no edge, at least not in the way you're imagining it. And if you have been in this channel before, you probably saw that coming. You know, I'm not going to give you a simple answer because the simple answer, there is no edge, isn't actually the interesting answer. The interesting answer is, what is there then? If you cannot hit a wall, you cannot fall off a cliff, and you cannot reach the end of the space, what is beyond? What does that word even mean? And the reason that's interesting, the reason I have been thinking about this for weeks and I'm still not over it, is that beyond the edge turns out to mean at least 8 different things, 8 different answers, depending on which question you're actually asking. Are you asking what can we see? Are you asking what can we ever influence? Are you asking is space infinite or finite? Are you asking what came before the Big Bang? Are you asking are there other universes with different laws of physics? Each of those questions give you completely different answer. And the deeper you go, the weirder it gets. So let's do this properly. Let's take each one of these questions seriously. Let's talk about horizons, not the metaphorical kind, but the actual physical boundaries in space-time that you can write down as equations. Let's talk about why the shape of the universe might mean you could fly in a straight line and come back to where you started. Let's talk about inflation, this explosive growth spurt universe had in its first moments, and why it almost certainly means there is vastly more universe beyond what we can see than what we can see. And then, this is where it gets really strange. Let's talk about what was there before the beginning, when even the word before stops making sense. So let's start with the most concrete version of this question. What is the farthest thing we can see? This has a real answer. It is called particle horizon, and it's about 46 billion light years away in every direction. Now, you might think, wait, the universe is only 13.8 billion years old. How can we see something 46 billion light years away? Wouldn't light from something that far take 46 billion years to reach us? And you'd be right to ask that. The reason the answer is 46 billion years and not 13.8 is that space itself has been stretching this whole time. The universe is expanding, so the light that left some distant galaxy 13.8 billion years ago, that galaxy is now much, much farther away. The light has traveled through expanding space, and by the time it reached us, the thing that emitted it was 46 billion light years distant. The particle horizon is the absolute limit of what we can see. It's the maximum distance light could have traveled to reach us since the universe became transparent, since the Big Bang basically, or very shortly after that. Anything beyond that distance, well, its light simply hasn't had enough time to get here yet. And here's the first thing that I want you to sit down with. That boundary is a causal boundary, not a physical wall. It's like the horizon on the ocean. When you are on a ship and you look out the horizon, you know the ocean doesn't end there. There is more ocean. You just can't see it because the earth curves away. The horizon is the limit of your perspective, not the limit of ocean. The particle horizon is the same thing. It's a limit of what we can observe. not a limit of what exists. But there's another horizon, and this one is much, much harder to think about. It's called the cosmic event horizon. The particle horizon is retrospective, it's about the past. How far has the light traveled to reach us so far? The event horizon is about the future. It asks if we emitted a signal right now, today, a beam of light, a radio transmission, anything, what is the maximum distance that light could ever reach, even if we wait infinite amount of time? And the answer is about 16 billion light years. Beyond that distance, the signal that emitted today will never reach its destination. Not if you wait a trillion years, not ever. Why? Because the expansion of the universe is accelerating. Dark energy is pushing galaxies faster and faster away. And there are regions of space that are receding from us so fast, faster than light effectively, because it's space itself that's expanding, not the thing moving through the space. That the light emitted from here can never ever catch up to them. There are regions in the universe, real regions, full of galaxies, stars, and presumably planets, and who knows, maybe other people having dinner table conversations about the exact same thing, that are causally disconnected from us forever. We cannot see them, we cannot signal them, we cannot interact with them in any way. They're real, but for all practical purposes, they might as well be in another universe. And here's the thing that really gets me. This number, the event horizon, it's smaller than particle horizon for a universe like ours. A particle horizon is 46 billion light years. The event horizon is 16 billion light years. This means that there are things we can see right now, galaxies whose ancient light has already reached us, that are already beyond the event horizon. Light we emit today will never reach them. They are slipping away from us in real time across causal boundary. We can see them, but we can never touch them. This is what cosmologists mean when they talk about beyond. In its most conservative, least speculative form, beyond just means space-like separated portions of the same space-time. Regions that are real but not currently observable, regions that don't violate any laws of physics, because no signal is outrunning the light cone. They're just separate, cut off from the geometry of expanding universe. And here's the honest truth. The most likely answer to what is beyond the observable universe is simply more universe, more of the same cosmic space-time, more of galaxies, more stars, more of the same laws of physics, stretching on and on, possibly forever. But, and this is where it gets genuinely interesting, we don't actually know that. Because general relativity, the theory that governs space and time, tells us local geometry of the universe, how space curves in response to matter and energy. It does not tell us the global topology. It does not tell us whether space is infinite or finite, whether it warps around itself, whether flying in a straight line brings you back to where you started. And that question, the shape of the entire universe, is completely different kind of beyond. Let me give you an analogy. Think about the surface of Earth. It's a two-dimensional surface. You can walk north, south, east, west. But the surface itself curves. It's a sphere. It's finite and the surface area is fixed. But it has no edge. You can walk forever and never hit a wall. And if you walk far enough in a straight line, you come back to where you started. That's what we mean by finite but unbounded. A surface that has fixed size but no edge. Now, take that idea and add a dimension. What if our three-dimensional universe is same? What if space is finite, fixed volume, but has no boundary? What if you could get in a spaceship, fly in a straight line long enough, and eventually come back to where you started? This is not science fiction. Physics allows for this. The math works perfectly. The simplest example is something called as 3 torus. It's hard to visualize because our brains aren't built for 4-dimensional geometry, but the idea is this. You take a cube of space and you identify the opposite faces. meaning if you exit through the right face, you instantly reappear through the left face. Like an old arcade game of asteroids. If you go out in one side, you come back in the other side. A 3 torus universe is finite. It has definite volume. It has no edge, no boundaries, no walls. And if you traveled far enough that you cross the entire volume, you would return to your starting point. You would see your own galaxy in the distance from the other side. And if you looked far enough with a telescope, you might see the same galaxy in different directions, different images of the same object. Light that traveled the short way, light that traveled the long way, light that went all way round. Now, here's where it gets real. We have actually looked for this. The Planck satellite, which mapped the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang, conducted a dedicated search for what are called mashed circles. The idea from a famous 1998 paper by Cornish, Spergel, and Stockman is this. If the universe is a finite multiply connected space, and if the scale of that topology is smaller than the distance to last scattering surface, the surface where the CMB was emitted, then that surface would intersect with itself. You would see the same patterns, the same circles in different parts of the sky. Planck looked hard. They found nothing, no matched circles, no repeated patterns, no evidence that the universe warps around the scales smaller than what we can observe. For a cubic torus, Planck ruled out any topology scale smaller than about 97% of the distant to last scattering surface. In other words, if the universe is 3 torus and if it is finite but unbounded, the cell you would have to cross to return to your starting point is larger than our entire observable universe. So maybe it's finite, maybe it's infinite. We genuinely cannot tell. The horizon, the particle horizon, prevents us from seeing far enough to know. And this is the first major open problem in cosmology, by the way. Even if our standard model of cosmology, the ACDM inflation, all of it is perfectly correct, in our observable patch, it does not tell us whether space is infinite or compact. It doesn't tell us whether we are in an infinite cosmos or a finite one with size just above our detection threshold. That's called the global underdetermination. The data cannot decide between radically different global realities. And that's not a failure of the theory. It's a consequence of living inside a universe where light takes time to travel and we can only see so far. Now let's talk about why we think there are more universes beyond the horizon in the first place. In 1981, a young physicist named Alan Guth proposed something radical. He was trying to solve few puzzles in the cosmology, why the universe looks so uniform in every direction, why it's so close to being spatially flat. And his answer was in the first fraction of a second after Big Bang, the universe underwent a period of exponential expansion, inflation. In about 10 to the minus 32 seconds, the universe expanded by a factor of at least 10 to 26. That's 1 followed by 26 zeros. Every distance in the universe was stretched by that factor almost instantaneously. Now, here's the key point for our question. Inflation was not a local event. It didn't happen in one little patch and stopped. The simplest and the best supported models of inflation says that once inflation starts, it's extremely hard to stop it everywhere. In most of space, it keeps going. Only in tiny pockets, bubbles, it does slow down and reheat into a normal expanding universe like ours. What if that's true? What if the entire observable universe is just one such bubble? Then the full universe that inflation created is vastly, incomprehensibly larger than what we can see. The most conservative extrapolation is what we have been calling more of the same. Beyond our horizon, there is simply more FLRW universe. More of the same cosmic space-time, same laws, same physics, same distribution of matter. No special boundary, just more. This is sometimes called as Tegmark's level 1 multiverse, and it's actually the least speculative version of the multiverse idea. It does not require new physics, it's just straightforward consequence of the inflation plus the fact that we can only see a finite volume. If the inflation happened here, it happened everywhere. The universe it created is just much bigger than our observable patch. But inflation doesn't stop at a level 1. There is a more radical version called internal inflation. In this picture, inflation never truly stops. Quantum fluctuation randomly cause regions to stop inflating and become more normal universes like ours, bubble universes, while the space between them keeps inflating forever. New bubbles constantly nucleate. Some grow, some collapse. The process never ends. And here is where it gets wild. These bubbles can have different physical constant. When inflation ends in a bubble, the energy of the inflation field, the field driving the expansion, gets pumped into particles and radiations. That's reheating. It's the hot Big Bang. But the details of that process, which particles gets produced, what the strengths of fundamental forces end up being, can depend exactly how inflation ended in that particular bubble. So our bubble got the constants we have. Electron has this mass, strong force has that strength, cosmological constant is this tiny number. But other bubbles might be different, radically different. Universes where stars can't form because gravity is too strong. Universes where atoms can't hold together. Universes that are completely dark or completely bright or populated by physics we can't even imagine. And these bubbles are not alternate dimensions, they are real physical dimensions. They are real physical regions embedded in same inflating space-time that gave birth to our universe. They are just causally disconnected from us forever. This is Tegmark's level 2 multiverse, and it's a lot. There's a paper by Tegmark from 2003 that lays out 4 levels of multiverse, and it's worth mentioning how ladder climbs level 1 more space, just more FLRW universes beyond our horizon. Same laws, different initial conditions. You probably exist out there actually. In an infinite universe, every possible arrangement of particles repeats eventually. That's not mysticism, it's combinatorics. Level 2, bubble universes from internal inflation, same fundamental laws, presumably, but different effective constant in each bubble. Physics is the same at the deepest level, but the expression of that physics varies. Level 3, the many-world interpretation of quantum mechanics. Every quantum event branches the universe. This one is, in Tegmark's framing, actually less speculative than level 2 because it only requires universe quantum mechanics, which we already have. But the interpretation is radical. Level 4, all mathematically possible structures exist. Every consistent mathematical framework corresponds to a real physical universe. This is the most speculative. Tegmark himself admits it. Now, I'm not going to spend a lot of time on levels 3 and 4. They're fascinating, but they are philosophy more than physics. At least for now, what matters for our conversation is this. Level 1 and level 2 are direct consequences of inflation, which is our best tested theory of early universe. They are not certain, but they're not crazy either. Alright, let's go deeper. All of this inflating bubble universes, the vast cosmic landscape, still assumes there's a classical space-time to talk about. But what was before that? What about the beginning itself? So here's the problem. In 2003, three physicists, Bord, Guth, and Valenkin, proved a theorem. It's called the BGV theorem and says something uncomfortable. Any universe that is, on average, expanding cannot be extended infinitely into the past. There must be a past boundary. Classical spacetime must have had a beginning. This doesn't necessarily mean singularity. It's a point of infinite density and curvature where physics breaks down. But it does mean that classical description runs out. Geodesics, the paths that light and matter follow, cannot be extended indefinitely backward. At some point, the classical picture fails. The Big Bang in this view is not point in the spacetime. It's a boundary of spacetime. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't quite work unless you switch the quantum mechanics. Quantum cosmology is exactly this, the attempt to describe the universe when classical spacetime isn't available anymore. Instead of a classical geometry, a single boundary, you can have a wave function, a quantum state of the entire universe. There are two famous proposals for what this might look like. The first, from Alexander Vilenkin in 1982, is called the tunneling proposal. The idea is that the universe nucleated quantum mechanically from nothing. Not nothing as empty space, but space doesn't exist yet. Nothing as in no space, no time, no matter, no geometry. The universe simply tunneled into existence. A quantum event governed by the Wheeler-DeWitt equation, which is basically the Schrodinger equation for the whole universe. And the result was a tiny inflating seed that became everything. Second, from James Hartle and Stephen Hawking in 1983, is the no boundary proposal. Instead of a singular beginning, they proposed that if you go back far enough, time becomes Euclidean. It became a fourth spatial dimension. There is no t equals 0 boundary. Universe is a smooth, closed geometry, like a surface of a sphere, but in four dimensions. Just as the Earth's surface has no edge, the universe has no boundary picture, no beginning, no edge. It's finite in the past, but with no boundary. In this picture, asking what happened before the Big Bang is literally asking what's north of the North Pole. The question has no referent. Now, the honest answer is that we have no idea which of these is right, or if any of them are. Quantum cosmology is not experimentally tested. The no boundary proposal and the tunneling proposal give different predictions for the wave function of the universe. But we can't measure those predictions. Not yet. Maybe not ever. The BGV theorem tells us classical spacetime had a beginning. But what happened before that beginning, what replaced the classical description, is one of the deepest open problems in physics. And this is where beyond the edge stops being geometry and becomes quantum gravity, where the very concept of space and time dissolve. And I find this genuinely beautiful. Not knowing, having the mathematics point of the boundary and then say, beyond this point, you need a new map, a map we haven't drawn yet. Let me bring us back to the Earth, or back to the observable universe anyway. What does data actually say about all of this? The short answer is data strongly supports the very boring and standard universe. Planck 2018, the most precise measurement of the cosmic microwave background we have ever done, tells us the universe is almost perfectly flat. The spatial curvature parameter omega is consistent with 0 or within 0.2%. The primordial perturbations, the tiny density fluctuations that became galaxies, are nearly scale invariant, nearly Gaussian, nearly n-diabatic. English? The universe was extraordinarily simple. Bicep and the kick array, looking for the faint signature of primordial gravitational waves, the smoking gun of high energy inflation, have pushed the tensor to scale ratio R down below 0.036. That's tight. It rules out the simplest large field inflation models. It favors quiet, gentler inflationary scenarios. Planck searched for matched circles, no detection. Searches for bubble collision signatures in CMB, no detection. Searches for superhorizon anomaly, no compelling evidence. Searches for any non-trivial topology below the scale of observable universe, no detection. Everything we can measure says our patch of universe is simple, standard, boring, and consistent with the most conservative version of standard model. Now, and this is crucial, this does not mean nothing is there. It means that whatever is beyond our horizon, it doesn't obviously spoils our patch. It doesn't leave obvious fingerprints. A vast, rich, complicated multiverse could exist just beyond our particle horizon. Different bubbles, different physics, different everything, and we would have no way to know. The horizon would keep it hidden. The same data that gives us such precision about observable universe leave the global ontology, the true nature of all that exists, almost completely undetermined. And there's something about that I find not frustrating, not scary, I don't know, maybe humbling is the word. We have built this extraordinary machinery of observation in mathematics. We can measure the geometry of the entire observable universe to one part in 500. We can trace the history of cosmic expansion back to a trillionth of a trillionth of a trillionth of a second after the Big Bang. We can write down the equations that describe the horizons of topology and quantum nucleations. And still, the most fundamental question you could ask about reality, how big is it, has no answer. Could it be infinite? Could it be finite but larger than we can see? Could it be one bubble in internal form of universes, each with different laws of physics? Could it be a quantum fluctuation from literal nothingness? The data doesn't tell us, and it might never tell us. But here's what I keep coming back to: the fact that we can ask these questions at all, that a species of apes to a small rocky planet can look up in the night sky, build an instrument to measure afterglow of creation, and write down mathematics that describe the shape of all space and time. That's extraordinary. We are inside the thing we're trying to understand. We are embedded in the geometry, and we have still managed to see almost all the way back to the beginning. We have mapped the causal boundaries to our existence. We have proven the classical spacetime had a start. We have seriously proposed that the universe might be one bubble among infinitely many. The edge isn't a place you can fly to. It isn't a wall. It is not a cliff. The edge is the limit of knowledge, a horizon in the deepest sense. It's a boundary between what we can know and what we can only wonder about. And I think that's kind of perfect actually, because if a universe had a literal edge, a cosmic wall, a sign saying end of space, that would be a smaller mystery, a soft thing. But this, a universe might be infinite or finite, might be unique or one of many, might have a beginning from nothing or might have no beginning at all. This is the mystery that grows the more you look at it. The edge of the universe isn't out there. It's right here, in the gap between what our equations can describe and what our instruments can measure. In the question that survives every new observation. And maybe that's what beyond really means. Not a place, not a thing. So, just the next question.